Hello, and welcome to another lecture. Today, I want to talk about the computational complexity, the bit cost of linear partial differential equations. And this is joint work with Ivan Koswara and Gleb Pogudin and Svetlana Selivanova. So let me show you the slides. And this is going to be a two-part lecture. First, we're going to talk about the basics, and then the second part, I'm going to show you the proofs. So here you see the slides, and Ivan Koswara used to be a master student at KAIST. We conducted this work, and he's now a PhD student at Singapore National University. Gleb is assistant professor at l'IX, École Polytechnique in near Paris, and Svetlana is both associated with KAIST and with the Sobolev Institute of Mathematics. So here you see the DOI reference for that publication, and I'm going to show you the overview of this first part of the talk, which will take roughly 1 hour. So we'll start with a reminder of discrete complexity theory, like P versus NP, and with the notion of reduction that underlies the definition of completeness. Then I'm going to show you the real counterpart to this complexity theory. We're talking about real numbers, real functions, real sequences, and most importantly, real operator, which is going to be increasingly subtle to understand even the definitions make sense. Then we're going to talk about the complexity of some popular operators in calculus and numerics, which are going to be weak complexities defined here. The operators we consider as function maximization, function integration, function differentiation, and solving ordinary differential equation. And the subtle point here is to emphasize, here we talk about smooth functions, functions that are at least continuous, Lipschitz continuous, or C1 or C2, or even C infinity. Then this is a recap, and then finally we get to contemporary results concerning computability and uncomputability, both of ordinary and of partial differential equations, and then refine these from computability to complexity questions, which is our contribution. Namely, we have fully characterized the computational complexity of linear partial differential equations in the bit complexity sense in terms of classical discrete complexity classes P, sharp P, and P space, partial differential equations with constant coefficients, and partial differential equations with not necessarily constant coefficients, which turn out to make a significant difference in intrinsic computational complexity for solving such PDEs, as we're going to prove formally. In the second part of this presentation, we're going to talk about the proofs. They're not covered in this first part, and we're talking about further results such as polynomial time, computability, and other related tools in the proofs. And we close with a generalization of the spectrum problem and variants of the spectrum problem. This is going to be the second part. So that being said, let's start here talking about classical complexity and remind you of reduction. And I do that, but already have to announce that this is not going to be applicable when we talk about the real setting of real numbers, real functions, and operators. But I want to emphasize why this is not applicable. So let me remind you of that first. So In the discrete complexity class, we have this set of all finite binary strings indicated here by this rectangle. And we have a subset which we want to decide whether inputs belong to this subset L or not, whether they lie outside. That's a decision problem, inside or outside, yes or no, 1 or 0. And here you see the complement of that decision problem. This is the outside. And now let's say we have another such decision problem, another subset, and we want to compare the computational complexity of these two problems without knowing what is the complexity of any of the two problems. Still, we were able to compare the intrinsic computational complexity by the notion of a reduction. And this notion of a reduction dates actually back to Tarski in the computable reduction, decidable reduction. Maybe a reduction is a total function from finite binary strings to finite binary strings that translates positive instances to positive instances and negative instances to negative instances. It does not need to be injective, it doesn't need to be surjective, but it must kind of respect the two decision problems at hand, in the sense that yes instances, the first decision problem must be mapped inside the second, and the complement of the first must be mapped to the complement of the second. And the first observation that illustrates that is, as I mentioned, classical notion due to Tarski, is the reasonable notion is that it kind of respects decidability. If the second decision problem is decidable, and if the translation is computable, then also the first one is decidable, and thus justifying this kind of partial order symbol, meaning that the first decision problem is not harder than the second. It's at most as hard, less or equal in terms of computability hardness. Also, this notion is easily verified to be transitive. So if the problem L is at most as hard as L prime is at most as hard as L double prime, then indeed by composition one verifies straightforwardly that L is at most as hard as L double prime. So that's a notion of reduction, computable reduction. Now let's refine that, and this is the work of Stephen Cook. Refine that from the perspective of computational complexity by adding a cost restraint. Namely, we say that the reduction is a polynomial time reduction if the translation function can be computed in time polynomial in the binary input length. Right? So input is a finite binary string, and the length is denoted by n, and the computation must take a time which is at most polynomial in that binary length n until the output is presented. And again, the properties that we enjoyed from the qualitative computable setting do carry over generalized to this quantitative complexity setting, now indicated with a subscript p, namely that now it respects polynomial time decidability. If the second one is polynomial decidable, then also the first one is polynomial decidable, meaning that the first one is at most as hard up to polynomial time as the second one. And also transitivity carries over similarly. So that's the notion of polynomial time reduction that underlies the definition of NP completeness. So let me give you some example of a reduction. First, we consider the click problem. The click is a decision problem on graphs. Input is a graph and an integer k encoded in binary, and the decision problem asks whether or whether not this graph contains a k-click, a complete subgraph of k vertices. So that's a decision problem. So this, imagine this to be the L here, the set of all encodings of graphs combined with a binary encoding of an integer k. And another decision problem, which corresponds to L prime here, is independent set. which ask similarly whether the given graph, undirected graph, has k pairwise non-connected vertices. So these are two decision problems, and actually their computational complexity is not known. So this is just perfectly suited example for what we have discussed as an application. Namely, although their computational complexity are not known of click and independent set, still they can be compared, these complexities, namely one can see by constructing a polynomial time reduction from click to independent set and a converse reduction from independent set to click, it follows that both have the same computational complexity up to polynomial. But let me emphasize a third time, what the computational complexity is of both is not known, whether it's polynomial or exponential or is something in between. So let me illustrate that and show you the polynomial time reduction from click by showing you here an example instance of click. Maybe here's a graph. You see a graph here on how many, it's 9 vertices, right? 9 vertices. And let's say, for example, k is equal to 4. So this asks whether this graph has, in independent set, whether this graph has 4 vertices which are pairwise non-connected. And you see that this is a positive instance. A decision problem for this instance is to be answered with yes, because the red vertices are indeed 4 vertices that are pairwise non-connected. So this graph has 4 pairwise non-connected vertices, the positive instance of independent set. Let's consider also a positive instance of click. So this is again a graph on 9 vertices, and this graph contains 4 vertices that are pairwise connected, a complete graph of 4 vertices for click, namely the red vertices are pairwise connected, they form a complete subgraph. And so the relation between these graphs is, in this example, is that one is the complement of the other, namely whenever the first graph has an edge between 2 vertices, then the second graph does not have an edge between these 2 vertices. And vice versa, if the second graph does not have an edge between 2 vertices like these two, then the other graph has an edge. So the edge, the choice of edges, is kind of the complement for each other. And thus translating one graph into its complement is easily feasible in polynomial time, namely just switch the bits. For example, in the adjacency matrix of the graph, adjacency matrix has n squared entries, bits 0 and 1. So flipping these, that's polynomial time. And as we observed, this translation complementing the graph, flipping the bits in the adjacency matrix between zeros and ones, that results in positive instance of the independent set problem to be translated into positive instances of a clicks problem, and vice versa. So in particular, negative instances of independent set get translated to negative instances of click. So this is a polynomial time reduction from independent set to click. And since this translation is self-inverse, right, applying it twice, complementing one recovers the original graph, it's also the translation in the opposite direction, so that this is indeed 2 polynomial time reductions from independent set to click and back from click to independent set, which according to this observation means that they both have the same complexity, but their complexities are known. So this is a foundation of discrete computational complexity, and it has identified, so these two are equivalent up to polynomial time, and there are many more problems that have been established to be equivalent up to polynomial time to these 2 problems, and this gives rise to this famous complexity class NP. More general complexity theory has identified an entire zoo of complexity classes, and I'm going to remind you here of the most important ones for the rest of this talk. So the overall kind of universe that we're working in today is a set of all decidable decision problems, a set of all recursive decision problems. This is indicated by this gray oval shape. Anything outside of that is undecidable, such as the halting problem, but we will not focus much on undecidable problems for now. Within the decidable problems, there's a class P of polynomial time decidable problems, efficiently decidable problems, which has these nice closure properties you see here. Outside of P, there's a class of exponential time decidable problem. These are not necessarily efficiently solvable problems, but it includes, of course, the polynomial time decidable, and in turn is included in the at all decidable problems. Between these two complexity classes lies an entire hierarchy. For example, there's a class of decision problems which can be solved using a polynomial amount of memory, which can be shown to be again included in the exponential time decidable problems, and in turn includes the polynomial time decidable. And within that class P space, in turn, is the class NP that you probably know and have heard of a lot from the Millennium Problem. So these are some of the basic complexity classes, but I need to introduce another, maybe less known complexity class, because it will turn out to be highly relevant for when we talk about the computational complexity of numerical problems, and that's first let me emphasize that the complete problems, the hardest problems in these two complexity classes are these two classes, right? And then there's the class Sharpie that I already hinted at. This is a class of counting problems, okay? And this is not a class of decision problems, to be fair, but it's a class of function problems. For example, counting how many complete subgraphs of k vertices are contained in a given graph, or how many satisfying assignments does a Boolean expression have. So this is counting, not yes or no, but the answer is an integer. So this is a complexity hierarchy, and it's a hierarchy in that the sense that every larger class contains every smaller class, but whether this is a strict containment is mostly unknown for most of these complexity classes, although people generally conjecture that it is true. And here's within the polynomial time decidable problems, there's an even smaller class, the logarithmic space decidable problems, but again, not going to further detail here. So some example decision problems in this class NP complete are the click and the independence set problem that I mentioned before, or the Boolean satisfiability problem from the Cook-Levin theorem. Some problem that is complete for this larger class. Sharp P counting problem is counting how many satisfying assignments does a given Boolean formula have. This asks whether it has a satisfying assignment at all. This asks how many there are, and intuitively knowing how many there are also entails whether there exists one. If the number, how many there are, is strictly positive, that means if and only if there exists one. And in the complexity class P space, the example problem is totally quantified Boolean formula, but I'm not going to expand on that further. So these are some problems. Complete hardest for these complexity classes, that is characterizing these complexity classes in this sense. And what I really want to emphasize here is that all this theory, the classical theory of computational complexity, applies to and is limited to discrete decision and counting problems. Problems where the input is a finite binary string, or anything that can be encoded as a finite binary string, and where the output is either yes yes, no for decision problems, or where the output is an integer. It does not apply at all to problems where the input are real numbers or even real functions, because they are intrinsically infinite. It cannot be input in finite time, and there's also no point in talking about the binary length of such an infinite object like a real number or real function. So all the theory here that is based on binary input length does not apply as soon as we proceed to real numbers or real functions for input. The same for output. If we talk about outputting a real number, or we talk about putting a real function, this is not something that can even be done in finite time. So we cannot even, it does not pertain to the framework here, where the answer is either yes, no for decision problems, or where the answer is an integer, discrete for counting problems, not applicable to the continuous setting of numerical problems like integration or solving differential equations, which is exactly what I want to talk about. So after having convinced you that the classical theory does not apply, let us now move on to how this complexity theory can be extended or generalized or adapted, adjusted for the setting of real numbers, of real sequences, real functions, and real operators, because we want to talk about solution operators to differential equation. That's where we're heading for. Okay, so real number computability. I think there are at least three very reasonable ways of defining what it means to compute a real number, as opposed to, for example, an integer being a real number, being an infinite object. First example, the definition is to say that it must have a decidable binary expansion. Binary expansion is zeros, ones, zero, false or truth. So that's where the classical theory applies, and we can adjust that and say a real number, call that computable, if it has such a decidable binary expansion. Another reasonable definition is to say that the real number can be approximated by means of, let's say, floating point numbers with a mantissa, an, and exponent 2 to the minus n. So that's this definition, approximated up to arbitrary small error 2 to the minus n. That's a sense of approximating real numbers. And the third reasonable definition is approximating with arbitrary rational fractions, not restricted to powers of 2, but arbitrary. And also the error bound may be arbitrary as long as it tends to 0 and as long as it is computable, recursive. And notice that here all these definitions pertain to the discrete setting, namely here we talk about outputting integers encoded in binary. Here we talk about outputting rational numbers, that is fractions, integer numerators, integer denominators, both encoded in binary and here. So it's all about discrete computation, but now we have adjusted that, adapted that to the setting of real number computability in three arguably reasonable ways, and we're faced with a dilemma: which definition should we use when we now move on to study real number computability, as actually Alan Turing did in 1937. But fortunately, it turns out that we're not in a dilemma. Miraculously, right there, the first, this one, numerators, denominators, this one kind of corresponds to interval, formalizes interval arithmetic. And it turns out that we're not in a dilemma. We don't have to choose between these three definitions because they are actually equivalent. So that is also strong evidence that these definitions are reasonable, and we're going to use them interchangeably. I'm not going to prove the equivalence. This is a topic of a different entire lecture. I would like to mention also fourth, a definition that sometimes occurs in numerical papers, namely outputting a sequence of approximations that converges to the real number without such error bounds. And it turns out, Specker had formally proved that with a counterexample Specker sequence that the fourth notion is actually strictly and considerably weaker than the first three, which are equivalent. Namely, this corresponds to Oracle access to the halting problem and undecidable problem. So I'm not going to talk about that fourth definition any further. Instead, remember, we want to talk about complexity, not about computability. So, and this is where the things start to get delicate. The first observation is that the equivalence between A and B does not hold uniformly. There's no way of translating a Turing machine for deciding the binary expansion. Now the other way, there's not a way to translate a Turing machine producing this sequence into a Turing machine deciding this binary expansion, whereas the equivalence between C and B does hold uniformly. So that's where things start to get subtle. And moreover, when we now move from qualitative computability to quantitative complexity, then they're not even non-uniformly equivalent anymore. So long story short, when we talk about real number complexity, we're going to take the item B by saying that a real number is computable in polynomial time if such a recursive sequence can be of integers, of numerators, of dyadic approximations can be computed in time polynomial in n. So that's kind of adjusting the definition from computational complexity from the discrete setting to the real setting. Now the output only, right? Output is an entire sequence for approximation to real number. There is no input. And the time for outputting the sequence elements is required to be polynomial in that precision parameter. And observe that this is kind of looks like exponential precision, but actually it basically means that the first n binary digits are accurate, right? So the first n binary digits, and so this is kind of like a adaptation of discrete complexity, where also we talk about binary digit length, and here it's binary output digit length as a cost parameter. So that's real number complexity. And now we move on to talk about real function. First, computability, and second, complexity. But first, before that, let me catch up on generalizing computability and complexity from single real numbers to real sequences. What you see here, this is a sequence of real numbers with index j, and here our definition says that the machine must be able to output a double sequence of dyadic approximation that approximate the jth real entry in this real sequence with this up to error 2 to the minus n. So now we have two parameters, the sequence index and the precision index. So that's a definition that we use, where dn denotes a set of dyadic rationals with denominator 2 to the n, and d denotes a set of all possible dyadic rationals of arbitrary denominator. And the theorem says that the following are equivalent when we talk about real function computability. First definition is regarding a function as kind of a translation, machine converting any input sequence of such dyadic rational approximations into a corresponding input sequence of dyadic rational approximations for the value. Input approximation to the argument, output approximations to the value, in such a way, and notice that there's no correspondence between that should be an M here. There's no correspondence between the input position and output position. That's entirely up to the computation. So maybe the computation needs particularly high input precision in order to output very low output precision, but that's up to the computation. That's one reasonable definition for computing a real function. Another definition is output-only definition. That's a perspective of a real function as a static object, namely output a sequence of approximating polynomials, like in Weierstrass, right? Output a sequence of dyadic polynomials. This is finite. Every single dyadic polynomial is finite, right? Has a finite degree and therefore finite number of dyadic coefficients. So that this is really outputting a sequence of finite objects, but an infinite sequence that approximates the given function uniformly, the uniform norm up to error 2 to the minus n uniformly. So that's output only definition. This is a kind of a counterpart to the definition of outputting a real number. Now we output a real function. For real numbers, we output a sequence of rational or dyadic approximations. For real functions, we output a sequence of rational or dyadic polynomials. And the third definition involves the real sequences, namely that the real sequences of values of the function, right? So the function has real values, but on input only restricted to a countable set, namely the set of all dyadic rational is a countable set. So this is kind of like a sequence of real numbers, and the requirement is that this sequence must be computable, real sequence in this sense. So again, we have three reasonable definitions, and the third one we actually amend and make an additional requirement, namely that the function must have a recursive modulus of uniform continuity, where this modulus is a mapping from integers to integers, satisfying this condition, namely that whenever arguments are sufficiently close to each other, then also values must be sufficiently close to each other. So this is the definition, and observe that this is an integer function, so the classical definition applies here. And again, we can avoid the dilemma of choosing between these three definitions, because the theorem says that they're actually equivalent. And some consequences, I'm not going to prove that, it's sometimes called the computable Weierstrass theorem, but some consequences of that say that, observe, we have to focus here on functions with compact domain, because only such functions have a uniform modulus of continuity, which does not depend on x. It only depends on the distance between x and y, but not on x itself. So uniform continuity, that's why we restrict to compact domains. And some consequence of this theorem of equivalence, which I'm not going to prove, is that whenever the argument x is computable and the function is computable, then also the value is computable. So computable function map computable arguments to computable values. It's a kind of an invariance property, but not vice versa. And we're going to use that corollary actually for a definition in a few minutes. We're going to call that weak computability. So we call a function weakly computable if whenever the argument is computable, also the value is computable. But this is really strictly weaker than function computability. So that's about the qualitative setting, and let's now move on from the qualitative to the quantitative setting of complexity. Okay, so in complexity, we want to talk about polynomial time complexity, and for this purpose, again, we do have to choose among the three qualitatively but not quantitatively equivalent items, and we choose the first one. This is our choice here. We choose the first one as notion for computational complexity, namely that the approximation up to order 2 to the minus n must be output within time polynomial in n. independently of M. And remember, this should also be an M. So there's some kind of an independent of the input sequence. So this is a very strong condition. And then one can strengthen this corollary whenever the argument is computed in polynomial time and the function is computed in polynomial time. In this sense, A, then also the value is computed in polynomial time. And this latter condition leads us to another definition, weak polynomial time computability, which I'm going to return to in a few more minutes. So this is our definition, and based on a corollary. Another point to observe is that, well, whenever the function is computable, then by this equivalence, it admits a computable discrete modulus of continuity. If a function is polynomial time computable, then it admits a polynomial time computable, a polynomial modulus, not polynomial time computable, but simply polynomial modulus of continuity. I'm not going to prove, but I'm going to return to that later when we define computational computability and complexity of operators. And one final thing I'd like to record here for when we talk about operators on the next slide is that these approximating polynomials here for the item B. One reason why we did not choose item B for our definition of complexity, but item A, is because approximating a simple function such as the shifted absolute value function, right? This is a very simple function, and for all reasonable definitions, this should be considered polynomial time computable. But from approximation theory, it follows that approximating that already requires polynomial of exponential degree. So we cannot even input or output polynomials approximating that simple function up to error 2 to the minus n in polynomial time. And this is the reason why we reject this definition when it comes to complexity. It's only good for computability. For complexity, definition A is the appropriate one. And I'd like you to keep that in mind when we now try to find a definition jointly for operator computability and for operator complexity. Because operators, as you know, receive functions as input. Real functions receive real numbers as input and produce real numbers as output. This is our definition A. Real operators receive functions as input and produce functions as output. And functionals receive real functions as input and produce real numbers as output. And this is what we're heading for now. Right now, we want to define what it means to compute a real functional. So let's call such a functional lambda, and the input should be some function from a certain function space. And for reasons that I'm going to explain in a minute, we're going to consider the space of all one Lipschitz, that is non-expansive, total functions from the real unit interval to the real unit interval. Here you see the definition, set of all functions from the real unit interval to the real unit interval that are one Lipschitz. In other words, they are not expansive. This is a subset of this is a continuous set of continuous functions. And one reason we're taking that here, restricting to that, is because it's a compact subset according to Arzela-Ascoli. So it's kind of a generalization to functions here with compact domains. This is a functional or operator with a compact domain in the function space. And a reasonable definition is to generalize item A. Item A for real functions converts input approximations to output approximations, dyadic rational approximations. And here we convert dyadic rational input polynomial approximations to dyadic rational output approximations for real numbers. That seems like a reasonable way of generalizing this case from real functions to real functionals, where the input are functions approximated by dyadic polynomials and the output is a real number approximated by dyadic rational numbers. And that is a very good definition, actually. For example, whenever this is computable, functional, and on a computable argument function, then also the value is computable, so we have the same properties. But now we want to generalize or refine that from qualitative computability to quantitative complexity. Then things start to become subtle, because remember, we cannot even input approximation to such a simple function in polynomial time as terms of polynomials. So this is not a good definition for operator complexity. It's a good definition for operator computability. When we talk about operator complexity, there's an entire direction of research pursued, for example, by Stephen Cook and Akitoshi Karamura. But here, for the purpose of this talk, I'm going to instead avoid that subtleties and focus on, right, this is compact. Instead, I'm going to focus on weak complexity for operators. Remember what it means. Weak complexity, it means whenever the function argument is polynomial time computable, then also the real number value is to be polynomial time computable. And that's what we're going to do here. Namely, we're going to find weak complexity. No mentioning of complexity of operators anymore in this talk, only weak complexity. If I forget to mention weak complexity, please insert the word weak everywhere when we talk about operator complexity. Everything is weak. And what does it mean to be weakly computable? Again, it means that whenever the function argument is computable, then the value real number must also be computable. And weakly computable in polynomial time is whenever the input function is computable in polynomial time, in the sense we talked about before, then also the value must be polynomial time computable real number. So this is now finally our definition of weak operator complexity, polynomial time complexity, which we're going to investigate in the setting from applying to operators like maximization, integration, solving ordinary and partial differential equations in order to understand our result characterizing the computational complexity of linear partial differential equations. So this is what I want to ask you to keep in mind, that polynomial time computable function must have a polynomial modulus. That's already a kind of information theoretic constraints on computational complexity. And now I'm going to report on some classical well-known folkloric properties of operators in calculus and their corresponding computability and complexity as a preparation for our own new results on computational complexity of linear partial differential equations. So the operators that had been considered long ago in this area involve integration. So here we see indefinite integration, right? Taking a function and taking its antiderivative, which is again a function. So this is an operator. And this is a computable operator. Same parameterized maximization, taking a function and returning the maximum of that function up to a parameter x, which varies. So the output is again a function. This is again a computable operator. Uncomputable operators include, for example, differentiation. There's a famous counterexample, namely computable, continuously differentiable function whose derivative is not computable. So we must be very careful when we talk about differentiation in a rigorous setting, not to mention automatic differentiation. And this is to keep in mind. On the other hand, when the function is polynomial computable and 2 times continuously differentiable, then its first derivative, which is still C1, is again computable. And similarly for polynomial time computability is preserved when the input function has this sufficiently high degree of regularity. So these are classical results And now let's move on to the more advanced setting of complexity and of differential equation. So what operator do we want to consider next? First, we want to refine these computability statements A and B. Similarly, in the complexity setting, then one can show whenever f is not just computable but polynomial time computable, then its parametric maximum is again polynomial time computable, provided, and here things start to get really interesting, provided that the millennium problem has a positive answer, provided that p is equal to np. Okay, so that's interesting. I'm not going to prove that, but what is even more interesting is that this is optimal. Right, so just a sketch of the proof is discretize the input function according to its modulus continuity, and then guess the maximum of that discrete and thus finite, exponentially large but finite number of values. And as I said, this is optimal, namely there exists a polynomial time computable function such that the maximum is not polynomial time computable unless p is equal to np. This is a, how to say, this means this is a numerical characterization of the p versus np millennium problem. Or put differently, in general, we cannot expect to calculate parametric maximum of even for functions unless p is equal to np. And what is even more striking is that this also applies to a smooth function. I'll go back to that later. But this second item, this optimality, and the first item were actually proven first by Kerr Co. Together with Harvey Friedman, famous logician. So this is kind of a p versus np problem, corresponds to the continuous, right, important continuous parametric maximization problem, which is kind of surprising if you think about it. I'll go back to that in a minute. Let's now look at the similar refinement of complexity theory of integration, parametric and definite and indefinite. So whenever f is polynomial time computable, then its parametric integral, indefinite integral, is again polynomial time computable, provided that now we have a stronger hypothesis, not just that p is equal to np, but that p is equal to sharp p, this larger complexity class. And here the proof is basically taking Riemann sum, and the step width must be exponentially small in order to guarantee the resulting output approximation. And again, this turns out to be optimal. There exists a polynomial time computable function such that the indefinite integral is not polynomial time computable unless this even stronger hypothesis holds. So from this perspective, indefinite integration is even harder than parametric maximization in that it corresponds to this significantly larger discrete complexity class than this one. And perhaps even more surprisingly, let's first look more closely at the integration problem, not just indefinite parametric, but also definite integration with bounds 0 to 1. Here we can slightly relax the hypothesis, namely from fp equal to sharp p onto the unary counterparts. Now, for those of you who are not familiar with the subtleties of discrete complexity, well, maybe already sharp p we considered something new. Here we have this index 1, which means unary input, but I'm not going to go further into that. The difference between these two classes is maybe not so large, and they can be related to other problems like non-deterministic exponential time is equal to non-deterministic to deterministic exponential time. And again, this characterization of definite Riemann integration in terms of this correct complexity class has been shown optimal. Namely, there exists a polynomial time computable function that this definite integral is not polynomial time computable unless these two complexity classes agree, which most people think they don't. So where do all these results come from? And even more striking, they generalize even to C infinity functions, so infinitely often continuously differentiable functions, not to analytic, but to so-called smooth function, which is even more surprising if you think about it, since we have all these efficient algorithms like Newton-Raphson integration, or Newton-Raphson root finding, maximization, and what does help is analyticity. So if we proceed here from smooth, from C infinity functions to functions that have local power series expansion, then all these operators do preserve polynomial time computability unconditionally without such hypothesis. But when we just take this little tick away from analytic to C infinity, then they don't. Then all these operators are hard in this weak sense, right? So we never speak about how input f is input and how the integral, which is a gainer function, gets output, but we fix that whenever f is polynomial time fixed, then this other function is again polynomial time computable or not. That's the weak complexity setting of these operators. These are results that were sorted by Kerry Coe and Howie Friedman since the 1980s, and they have spawned many more results. I'm going to report some more of this in the next slide. But to simplify notation, let's just say and combine these two claims. Whenever it's f is polynomial time computable, then also the indefinite integral is polynomial time computable, provided fp is equal to sharp p, and this is optimal. Let's combine that with a statement that indefinite Riemann integration is sharp p complete, but keep putting the quotes here because all the notions of completeness, remember our initial first slides, only apply to the discrete setting. All the notion completeness is based on reduction, and reduction only applies to decision problems or to discrete counting problems, not to this continuous setting. So anybody that talks about complete problems or real numbers of operators must be taken with particular care, because completeness by its very definition is intrinsically limited to the discrete setting, and as we've seen, cannot be easily translated to the continuous setting. So let's similarly summarize the complexity result for a definite Riemann integration as sharp P1 complete, but with these quotes to emphasize. And remember that smoothness does not help unless we proceed from smooth to analytic. And the last, about maximization being NP complete, we also summarize that in this sense. That will make talking easier. And as I said, Newton-Raphson, which is very good for maximization, but it requires a good starting point. And where do you get this good starting point? Well, you can guess one, and that's exactly what NP is about, guessing good starting points. That's where the guessing re-emerges in the NP setting. And I must emphasize one final time, this is all about weak operator complexity, where the input function is not really presented to a computer, but is arbitrarily fixed. There's no input, and also output is just the resulting function or the resulting real number. Okay, so now we're almost up to speed to talk about differential equations. I do mention that these quotes, the completeness and reduction can be made formal, both computable reduction and polynomial time computable reductions among the continuous problems have been defined and studied first by Koswara in 1992. Many successor works, for example, here's a very nice survey by Vasco Pato and Guido Gerardi from 2011 in the computable setting, the continuous setting, qualitatively and quantitatively, as I mentioned, Akitoshi Kawamura and Stephen Cook in 2012. But this is a subtle definitions and beyond the purpose of the present talk, because I want to go forward and finally get to even state our results, and we're almost there. Just some final slide before that about known results about ordinary differential equations. And to keep in mind, we talked about parameterized continuous maximization being NP complete in quotes, definite smooth Riemann integration being sharp P1 complete, and indefinite smooth Riemann integration being sharply complete, with this picture of computational complexity classes NP beyond lower than sharp P, and here we have even larger class P space, and the one with index 1 is imagine it to be a little bit here inside of sharp P for intuitive purposes. And now we can start looking at ordinary differential equation before we finally conclude this first part of the talk with our results concerning partial differential equation. So here you see a first order differential equation with initial condition, and Prell and Richards pointed out that there exists computable functions f such that this ODE has many but no computable solution at all. So we must be really careful. This essentially is due to the non-uniqueness of Cauchy-Peano's existence theorem when the right-hand side is only continuous. When the right-hand side is actually Lipschitz continuous, then we know classically that the solution is unique, and one can show that it's actually computable. For even further, it's computable in polynomial space if the function f is polynomial time computable. That's basically an analysis of the Euler method refinement of Picard-Lindelöf. Remember, Euler method is time discretized, but in order to guarantee output approximation error 2 to the minus n, the time step width must be exponentially small, also 2 to the minus n roughly, depending on the smoothness of the function, which means exponential time, but we can reuse this, and during the iteration, exponentially many iterations, each stage only uses polynomial amount of memory, and thus this is in P space, not in exponential time, even in P space, which is an improvement. So the analysis of the Euler method shows not just exponential time, but polynomial space. Now, this has been observed in, I think, 1990 or 1991 by Kerry Cole. And Kerry Cole asked, is this optimal? Is Euler methods optimal, or can we do better than P space in terms of this complexity hierarchy? And this question remained open for 20 years until Akitoshi Kawamura indeed proved P space is optimal. He constructed very carefully and smartly Lipschitz continuous polynomial time computable right-hand side such that the solution to this ODE unique solution is not polynomial time computable unless P time is equal to P space. So it's kind of P space optimal, solving Lipschitz continuous differential equations, and 4 years later he generalized and extended that from Lipschitz to C1 right-hand side, continuously differential right-hand side. And I mentioned that because we're actually going to need that today in the second part when we talk about PDEs. So let's keep that in mind, that solving ordinary differential equation in this sense with all these quotes is p-space complete. It's even harder than Riemann integration, which is even harder than maximization in the continuous setting of C1. It's open whether this can be generalized to C2, whether C2 is still as hard, but C2 is at least as hard as the counting hierarchy, which I'm not going to introduce further. So this is a computational complexity, weak complexity of solving ODEs, nonlinear ODEs with C1 right-hand side. And now, finally, we get, and this is going to be the end of our first part of the talk, to partial differential equations, to linear partial differential equations. Let me give some examples, kind of prototype examples of linear partial differential equation. There's a Laplace equation, which is like this. So you see here, second order spatial derivatives, and I should omit the t here. This is not time dependent. This is a prototype of an elliptic partial differential equation. The heat equation is a parabolic one, similar right-hand side, second order in space, and the left-hand side is first order in time. 0 here refers to temporal derivatives. And the wave equation, prototype of a hyperbolic partial differential equation with second order derivative in time. So these are the equations here. And let's first look at the computability. Again, we have to be careful. Borel and Richards proved that constructed a computable initial condition to the wave equation with an uncomputable solution. Yes, that was quite a surprise with a uncomputable classic solution. But the experts in PDEs know that classic, that is the uniform approximation, is not the right way of treating the wave equation. Better way is to consider it in the Sobolev sense, and Weyrauch and Song has shown that in the Sobolev sense, the Weyrauch equation is a wave equation. Thus is computable, maps computable arguments to computable solutions. These are linear different PDEs. I briefly mention self-promotion, also an example result about nonlinear PDE Navier-Stokes, which we were able to show to be computable in the L2 sense, not in the strong sense. But let's return to the case of linear PDEs and consider a general evolutionary PDE. So here we have first order in time. The wave equation can be brought into this form by introducing an artificial new variable, kind of splitting up this second order differential operator into two first order. So that's the left-hand side, and the right-hand side, generalizing this, could be a combination of partial derivatives of various orders. So this J here is a multi-index. First part means how often to differentiate with respect to the first spatial variable. Second component says how often to differentiate with respect to the second spatial variable in case where X ranges over some high dimensional Euclidean space. So this is an evolutionary partial differential equation. It's linear and it has coefficients that are either real numbers or matrices, depending on whether this is a vector system or a scalar PDE. And these coefficients may or may not depend on space. We prohibit them from depending on time, but again, this can be this is no loss of generality by introducing another additional artificial spatial variable. And the domain of these PDEs is going to be called omega, a subset of Euclidean space, and we're going to have an initial condition at time 0. So first order means we only need one initial condition, which is a function, scalar or vector valued. This is the initial condition. And to simplify things, we're going to restrict to a periodic boundary conditions. So remember, we need to restrict to compact domains anyway to even talk about complexity. And here we're going to take the torus, d-dimensional torus as domain, which means things wrap around at 1 back to 0 in all d directions. And boundary that boundary conditions means not just the function values for initial condition and for solution and for the coefficient functions must satisfy this, but also their derivatives must wrap around basically. So that's our setting to talk about computational complexity, periodic boundary conditions. And so this is the homogeneous setting. Here you see the inhomogeneous setting, which is called the Poisson equation here. And yeah, that's a kind of a linear evolutionary partial differential equations we considered. And our results this is the final slide. Remember, we have characterized Sharpie with Riemann integration, Sharpie1 with definite Riemann integration, ODE solving, nonlinear ODE solving, p-space complete. And previous work has shown the Laplace-Poisson equation to be, in a sense, between Sharpie and Sharpie1. So this is this equation. And what we proved is the heat equation also lies between Sharpie and Sharpie1. That's items C and D of our work. So we've kind of extended this known result from 2017, Akitoshi Kawamura and my then PhD student Florian Steinberg, from the Poisson to the heat equation and beyond. I mean, this is finally the final slide, our contribution. We have shown first when the coefficient functions here are polynomial time computable, then the solution to this PDE is computable in P space in higher dimensions. So this is a generalization of these results, and observe that ODE here, P space for nonlinear, but here we're talking about PDEs, which intuitively are more complicated, but only about linear PDEs, which again is less general than the nonlinear ODEs. But it turns out in the end, it does result in P space only, provided here we have some technical hypothesis, namely that the PDE admits a so-called stable finite element method, a difference scheme that converges to a classical solution. That's our technical convergence hypothesis. And we show, that's something we're maybe most proud of, we show that this is optimal. P space is optimal. There exists polynomial time computable coefficient functions such that the solution cannot be computed in polynomial time unless P is equal to P space. So corresponding similar to the ODE case, but this ODE case is nonlinear. Here we're talking about linear partial differential equations. Now, our third result generalizes the one about the heat equation, namely whenever the coefficient functions are constant, not functions, but independent of space, they're already independent of time, but if they're already additionally independent of space, like it is the case for the Hickel equation, see, here the coefficients are simply 1, right? Then the solution to this PDE, linear PDE, can even be computed in Sharpie, which is lower complexity class. Remember, this corresponds to Riemann integration. And again, we can show this optimal where the heat equation requires Sharpie 1. So 2 main results: p-space for a linear PDEs with non-constant coefficients and optimal, Sharpie for linear PDEs with constant coefficients and optimal in the heat equation case. So these are our results, and that is all for today. For the first part, I'm going to give the proofs in the second part, and here you see a remainder of the complexity hierarchy, right? So p-space for general PDEs, Sharpie for those with constant coefficients, and this corresponds to Riemann integration. Also, this corresponds to nonlinear ODEs, and this corresponds to maximization, so characterization. And one final reminder, this is weak complexity. This is not where we input the coefficient functions. They are arbitrary but fixed. Also, the initial condition is supposed to be arbitrary but fixed. The only input is where we want to evaluate the solution, at what time, at what position, and up to what error. Namely, the output is only approximate the solution, that should be u, up to this, at this position in time and space, up to error 2 to the minus n. Again, we don't even output the entire function. We don't input functions, we don't output functions, we only output functions at the desired, the function value at the desired position. And in this way, we can beat the exponential running time and get down to p-space and even to Sharpie. So to summarize part 2, I've reminded you of discrete complexity class and reduction, and in particular why completeness does not, and the notion of completeness cannot apply to the continuous setting of real numbers, real functions, and real operators. Instead, we defined real computational complexity for functions, real functions, sequences, and operators. Weak complexity theory for operators. Classical statements about complexity of smooth maximization corresponds to NP. Smooth integration corresponds to Sharpie or Sharpie 1, depending on whether it's definite or indefinite. Differentiation can leave the realm of computability, and ODEs, if they are Lipschitz, corresponds even to the complexity class p-space, according to Akitoshi. We talked about computability and incomputability of ODEs. We need at least Lipschitz right-hand side, vector C1. And then we talked our results about the computational complexity of linear PDEs. Constant coefficient corresponds to Sharpie, and this is optimal. Non-constant coefficients correspond to p-space, and this is optimal. And next time, we're going to continue with part 2. We're going to talk, recap common numerical approaches to solving PDEs using these finite element methods, different schemes, our analysis of them using exponential linear algebra, dealing with matrices of exponential size, raising such matrices to exponential powers, and the computational cost incurred by them in order to develop a polynomial space algorithm for solving linear PDEs, and a Sharpie algorithm for solving linear PDEs with constant coefficients, showing Sharpie 1 optimal for the heat equation, showing p-space optimal for the general case, and some further results and tools that we used and needed and came up with along the way. And finally, I'm going to talk about the spectrum problem in real complexity and other settings. So that's all for today and for now. And I look forward to seeing you again in this part 2. So thank you very much for your attention. And that's the end for now.